So today we finished talking about the first intermolecular force that exists for covalent molecules. So now we're going to keep going with our conversation of intermolecular forces. And we said that the first one, or dispersion forces, is something all molecules have. The second intermolecular force is called dipole-dipole forces, and this is for polar molecules. So we know that polar molecules have a permanent dipole, and this is called the net dipole. When we have a net dipole, or how do we decide that we have a net dipole? We know that we have a net dipole if we can draw the Lewis structure first. And after we draw the Lewis structure, we assign the molecular geometry and we assign the net dipole based on the Fonkelbrish. So this is something that we practiced extensively with Chapter 10, and we're going to keep using what we learned in Chapter 10 for Chapter 11. So if you draw your Lewis structure, look at the VSEPR sketch, and assign a net dipole in your molecule, then that molecule is polar and can have these dipole-dipole attractions with other polar molecules. So the difference between dipole-dipole attractions and dispersion attractions is that these are stronger. So with dispersion, it's a temporary dipole where our electrons kind of clump together. But with a permanent dipole or a net dipole, we have a partial positive on one part of the molecule and a partial negative on the other part of the molecule. And we know that opposites attract. So we can have those attractions with nearby molecules that have these opposite charges. And so this attraction is going to be stronger than just a molecule that only has dispersion forces. So what happens is you have a molecule with a net dipole, and so the side that the arrow is pointing to is partial negative. The side that doesn't have the arrow, or the arrow is pointing away from, has a partial positive. So if another nearby molecule lines up, then the partial negative is attracted to the partial positive. And you can imagine another nearby molecule. I'm terrible at drawing. We know that if you have another nearby plus and another minus, then those are going to be attracted to each other. So you have this extended network of these much stronger attractions. And so if you have a molecule that has a net dipole, then you will have a higher boiling point in molecules with dipole-dipole forces or attractions than with dispersion only. But they have to be really similar in size, because otherwise it doesn't work. Otherwise the size kind of competes with the dipole-dipole attraction. So we're always going to be comparing molecules with similar size to kind of simplify our conversation. So let's look at an example. If we have two molecules with pretty much the same molar mass, so you can see that these molar masses are basically the same, let's look at the structure of the molecule. So formaldehyde has this oxygen atom. We drew it in our discussion this week, and we know that this molecule has a net dipole towards oxygen. So this molecule is polar. Whereas this one, ethane, only has carbon and hydrogen in it, so there's no net dipole in this molecule, because we know that carbon and hydrogen have basically the same electronegativity. But look at our boiling points. So the boiling point of the one that has dipole-dipole forces, because it's polar, is going to be much higher than the one that has dispersion only. So it's a significant difference, right? A difference, math is hard, of about, 60, almost 70 degrees. And this happens because that polarity results in that very strong attraction to nearby molecules. So it becomes much harder to break them apart. And it's a similar situation with melting point. Melting point is where the solid goes to the liquid phase. But again, a very large difference in the energy that we need to break the attractions just because one molecule is polar and the other is not. The diagram underneath shows a little bit different scenario than what we're used to, but it's something we talked about in chapter 9 and 10 with dipole moment. Dipole moment tells us how polar is it. So if we have a bunch of molecules, we don't really even care about their structure. They all have about the same molar mass. So they're about the same size, but what we're looking at is increasing polarity. So polarity increases going to the right. And notice what happens is also the boiling point increases as the molecules go to the right. So what this shows us is that if we have a higher dipole moment, then our molecule is going to be more polar. And if it's more polar, then we have stronger dipole-dipole interactions. And if we have stronger dipole-dipole interactions, that also means that we are going to have a higher boiling point. So in these molecules here, we didn't have to draw them, okay? We could have just been given a name or a formula, but being given the dipole moment, all we had to do then was look at the dipole moment to know which one was going to have the highest boiling point. Let's move on to our last intermolecular force, which is hydrogen bonding. So hydrogen bonding is still a covalent intermolecular force. It is not a bond, but it happens when you have hydrogen with a very electronegative atom. So the very electronegative atom is bound to hydrogen. So there is a direct bond to hydrogen. What happens is the very electronegative atom is going to pull the electrons away from hydrogen by pulling them closer to itself, meaning away from hydrogen. What happens then is hydrogen becomes even more positive than just a traditional polarity situation. So what results is an even stronger dipole-dipole attraction because we have an even stronger partial positive and partial negative. What happens is the hydrogen is de-shielded, meaning its electron is pulled away from it. And so what happens is it almost acts like an exposed proton. So because it's so much more positive than a typical polar molecule, then we have a much stronger attraction. So this is stronger partial positive on the hydrogen. So it's a stronger partial charge, which means that we're going to have a stronger attraction to partial negative things. So hydrogen bonds only happen with our very electronegative atoms. And we know from the periodic table and Fonkelbruch that our most electronegative atoms are F, O, or N only. And I like to say that it's fun to do hydrogen bonding. So you have to have not just F, O, or N in your molecule, but you must have an FH, OH, or NH bond. And the attraction happens between the partial negative on H and the lone pair on the electronegative atom. And so the attraction, let's put it up here. So it's an attraction between the partial positive on H and lone pair on the electronegative atom. So molecules with hydrogen bonding have a much higher boiling point than molecules without it. And again, they should be of similar size because the size has a big impact on the dispersion forces. So let's look at an example here. In these two molecules, ethanol and dimethyl ether, they have the same formula and the same molar mass, but their structures are very different. So in the first one, we have this OH on the end. So we have O and then H touching it. So we know this molecule is polar. It has a net dipole. But so is this one. So since we have O right here, we know that this molecule is also polar, and the net dipole is going up towards the oxygen. But what's the difference between these molecules? The difference is here we have H connected to O. And because we have H connected to O, meaning we have an OH bond, we can do hydrogen bonding. And look at the difference in the boiling point. Almost 100 degrees different, even though they're both polar, even though they have the same molar mass. Look at how different the boiling point is, and that tells you about the strength of that hydrogen bonding attraction between those different molecules. So if we put two ethanol molecules together, we know that the partial negative on oxygen with the lone pairs is going to have a really strong attraction to the partial positive hydrogen. And the same deal with the partial positive on the hydrogen that's in the first molecule, it's going to have a really strong attraction to the partial negative. And so we are going to have a very strong H-bond attraction between these two ethanol molecules. And ethanol, you might know it as the alcohol that people drink, and that's one reason why people usually store ethanol in the freezer, is because it typically wait, that doesn't make any sense. Let me say that again. It shouldn't evaporate easily. Oh, it's because it doesn't freeze easily. That's why. All right, so you can keep it in the freezer. It doesn't freeze easily because of the melting point, and it also shouldn't evaporate really easily, so it's stable for a very long time. So basically the point of that whole conversation is that ethanol has a high boiling point, much higher than ether, because it has those strong hydrogen bonding effects. And dimethyl ether, if you've ever heard of it, ether, it's colloquially known as ether, and it has been used for a long time, or was used for a long time, to kind of knock people out. Or even diethyl ether, because it has a low boiling point. And if you put that on a cloth, somebody will inhale it and be knocked out shortly. And so it was used back in the day for surgeries because it's got such a low boiling point. So ethanol, hydrogen bonding, polar, much stronger intermolecular forces, much higher boiling point. Okay, so the thing about hydrogen bonding generally is that you don't actually have to have a net dipole in your molecule. So you can have hydrogen bonding even without dipole-dipole interactions. All you have to have is those bonds, either the FH, OH, or NH bond. The other thing that we know about hydrogen bonding is that you can actually form a hydrogen bond to a polar molecule as well. So you don't have to have hydrogen bonding in both the molecules that are attracted to each other. A hydrogen bond can happen with a molecule that's just polar because, again, we'll have that attraction between the partial positive and partial negative on the molecule that does have hydrogen bonding with something else with partial charges. The other thing that I've said a couple times is that hydrogen bonds are not actual bonds. There is no bond that happens between the atoms. It's just a very strong attraction. So it's an intermolecular force attraction, not a bond. And so it's much, much weaker than a covalent bond. The other thing that's really important about hydrogen bonding is that hydrogen bonding really accounts for the very unusual properties of water. So we know that water is super weird because water has a weird thing with density, where the density of the liquid is greater than the density of the solid. So we know that ice floats in water, but that shouldn't happen because with every other substance, it doesn't happen. But we know that that's important for life because otherwise all the fishies everywhere would basically die in the winter, but they don't because the ice forms on top. The other thing is water has a very, very high boiling point. It has a much higher boiling point than we would expect for something with its molar mass. So the molar mass of water is around 18 grams per mole. That's pretty small. That's smaller than some gases even. But because of that polarity and hydrogen bonding, water actually has a very high boiling point. And so we can look at how we know that water has the lone pairs on oxygen, and so those lone pairs pull even more of the electrons from the nearby hydrogen. So we have partial positive on our hydrogen, and we have the negative on our oxygen with the lone pairs. And so those things are going to be attracted to each other. So we've got those attractions between the negative and the positive. And that can happen in a really extended network throughout the water molecule, as is shown here. So if you look at this figure, we have liquid water. This one's not in your notes. I just wanted to show it to you. In liquid water, you have all of these dotted lines that show you the hydrogen bonding attraction between the hydrogen and the lone pairs. But what happens is, because water can move around freely, the hydrogen bonds constantly break and reform. So this will go away and a new one will form, and this will go away and a new one will form, and that constantly happens. So even though those attractions are strong, because water is always moving around, they don't stay constant. However, when we get into ice, you form these really stable, continuous networks of hydrogen bonds that stick around. And so it keeps water in a really organized pattern. And so this pattern is not as condensed, right? And so the pattern, because it's so stable, keeps those water molecules a little bit further apart, making it less dense, which is why ice floats. So let's look at a few examples now that we've covered all of the different attractions or intermolecular forces that we can have. So if we look at Cl2, Cl2 is a nonpolar molecule. It has no net dipole. And so because we have no net dipole, we have bonds between the molecules, but we don't have any dipole-dipole or hydrogen bonding. The attractions that we have here are when the electrons move just enough so that we end up with temporary dipoles. And so we can draw little tiny negatives and little tiny positives, and that's the attraction that we have. And so this is a dispersion force because those partial charges are very temporary. They happen and then unhappen regularly in just mere fractions of a second. Now let's look at HCl. So we know in the Lewis structure of HCl that chlorine is more electronegative, and so it has that partial negative charge. And so you end up with this pretty strong attraction between the partial negative and the partial positive. And that molecule, because it is polar and has a net dipole, we have that dipole-dipole attraction. Let's look at CH3OH. So this is methanol. So methanol, if we draw the Lewis structure, CH3 means we have 3 hydrogens on carbon, and then we have oxygen, and we know that oxygen has 2 lone pairs, so it's got to have this bent structure. And oxygen is more polar than any of the other elements, so the molecule overall, oxygen's more electronegative, so the molecule overall is polar, meaning it has a net dipole. And so the OH end of the molecule, where the O is the partial partial negative part of the molecule, and the H's are partially positive. And so we're going to have these really strong H bonding attractions between the H and the O of nearby molecules. So if we list all of the intermolecular forces that are present in this molecule, we still have dispersion, even though it's not really important. We do have dipole-dipole attractions because the molecule is polar, but the important one that contributes to the increased boiling point is hydrogen bonding. So we have all of those interactions there. If we look at CH2, CH3CH2, OCH2CH3, that is another example of an ether. And if you look at the molecule, you have a net dipole towards oxygen. And so this molecule is polar as well. And this molecule will still have dispersion forces just like everything else, but it also has a really strong dipole-dipole attraction between the partial positive end, which is the side that has the C and H groups on it, and the partial negative end, which is the side that has the oxygen in it. So this molecule is polar, and so is this one because they're the same, and we've got that plus minus attraction, and that is our dipole-dipole interaction. In our last example, we're just comparing the branched structure versus the more linear structure. So here we have a lot of attraction between these atoms, and so we're going to have stronger dispersion forces here versus the same molecule, same molar mass, but this one's branched, so we have weaker dispersion forces. And before we finish with this set of notes, what I wanted to do was show you how this shows up in biology. So in biology, we know that DNA is super important for everything in life. But what I wanted to show you is how those side chains pair up. So we know T groups and A groups pair up and C and G pair up. And the reason why those are complementary is because of the hydrogen bonding that happens between the NH group of adenine and the O of thymine. And then the NH group of thymine has hydrogen bonding attractions to adenine. If you pair up your C and G groups, cytosine has 3 hydrogen bonds to guanine, and that's why those two pairs are so complementary to each other. And again, that's really what holds together the strands of DNA. So this is just a picture of that for different sheets of polypeptide backbones. So it's just wanted to give you another visual of how that hydrogen bonding attraction happens in a very extended network in all these biological systems. And not only is it important when your cells are doing DNA replication, but also in different reactions. So we know that some proteins in the body do catalysis for reactions. And what happens is in the in-between steps of those reactions, we have hydrogen bonding attractions that make the molecule more stable and able to react. So this is not something you'd be tested on, but I just think is interesting to be able to see. And on Monday, we'll do some practice with all of these and talk about how things mix. Thank you and have a great weekend.